All right, as I told you guys, we need to get through a series of notes here, just a series of videos to cover some of those examples for stoichiometry you need to be able to do. So this new section, section 2, is about ideal stoichiometric calculations. Ideal means that everything's going to go through to completion. There are no limiting factors in these problems, although in the next section we will have limiting reactants, and you'll have to deal with that when it comes. But for right now, it should be fairly simple, fairly easy. You just need to be able to set up these problems and follow through, showing your work. So you just need to start off just looking at them. This first one says that hydrogen peroxide decomposes to form water and oxygen gas. So that's your reaction that you're dealing with. And you would just have to come up with an equation. So sometimes I'll give you the equation, sometimes you got to come up with it on your own. In this case, I have to write the equation myself. I got to make sure that it's balanced. Right now, I don't have the same number of oxygens on both sides. So I think if I double the water and I double the hydrogen peroxide, then everything will be balanced. There's 4 hydrogens on both sides, 4 oxygens on both sides. Should be good. The actual problem, though, is asking how many moles of oxygen would result if you started out with 5 moles of that hydrogen peroxide. So like I said before, you're starting out with a certain amount of something. Right? Sometimes I give you grams, sometimes I give you moles, but in this case, it's 5 moles of hydrogen peroxide. And all I want to know is how many moles of oxygen will be produced. So this one's actually pretty simple. I just have to do one thing. I have to do a mole ratio. I got 5 moles of hydrogen peroxide right now. I want to know how many moles of oxygen are going to be produced. So all you have to do is do a mole ratio that cancels things out. It's 1 mole of oxygen for every 2 moles of hydrogen peroxide. So this one's fairly simple, fairly easy, right? Moles of hydrogen peroxide cancels out. 5 divided by 2 is going to give me something like 2.5. All right, now I'm not too worried about sig figs. This would probably round to a 3. Since it started out with only 1 sig fig, it has to end up with 1 sig fig. So your answer would be 3 moles of oxygen. So this is as simple a problem as we can have in this chapter, going from 1 mole amount to another. Our next reaction, though, is a little bit tougher, right? We're just picking up one little step at a time. Sodium azide is activated in an airbag. Nitrogen gas, sodium are produced according to the following equation. So you have this solid sodium azide, that NaN3, that turns into sodium, solid sodium, and nitrogen gas. Since it's a 2 to 3 ratio with the nitrogens, I'm guessing I need to do my least common multiple. Then I get a 2 right here. Should all be balanced appropriately. But then you get into the actual stoichiometry. If I start out with 5 or half a mole, of sodium azide, what mass of nitrogen would I make in the end? So I need to start out with what I'm given, 0.500 moles. And just like that last problem, if you have moles, you just need to change it into moles of the other stuff. So my ratio in this case, since I want nitrogen, is a 3 to 2, because there's 3 of those, 3 moles of nitrogen for every 2 moles of the sodium azide. But I can't stop right there because I don't want moles of nitrogen as a product. I want the mass of nitrogen. So again, I need to multiply by a molar mass for that last step. Right? If I want a mass, pen's not working, of nitrogen, I need to recognize that 1 mole of nitrogen, diatomic nitrogen, would have a mass of 28.02 grams. I know that because it's 14.01 for one nitrogen, so two of them, 28.02. So if I set up my work like this, moles of sodium azide cancels out, moles of nitrogen cancel out. I get an answer that's a mass, a grams of nitrogen. This is all I should need to do. So all I have to do now is multiply and divide. So I know in this case that I'm going to take half of 28.02 from the get-go, 0.5 times that would be that 14.01 again. Divide that in half and it'd be like 7.005, and then take that times 3, it should be 21 or something like that. So I'm going to grab a calculator here real quick just to make sure, but 0.5 times 3 times 28.02 divided by 2 gives me an answer of 21.015. Again, you need to use sig figs in problems like this, and since the original number only had 3 sig figs, I'm going to round. So my 21.015 with 3 sig figs is just a 21.0 grams of nitrogen. And that would be my answer for this one. So one step up, the last one I only had to do 1 mole ratio. This one I had to do a mole ratio and I had to multiply by a molar mass. But you can have all sorts of looks to this, but it takes on a pattern that you should be able to recognize pretty quickly. So we'll go on to the next problem here. Sulfur dioxide is an unwelcome result of burning soft coal in power plants. Some of the sulfur dioxide ends up as sulfuric acid in rain. Net reaction is as follows. So I have the reaction already, I just need to balance it. I'm going to have to look real quick. It actually looks like I'll have 1 too many oxygens, which makes this a little inconvenient, but we can get it figured out. So if I have too many oxygens on the left side, I'm probably going to need to make at least 2 of these. So I'm going to gamble there, see if that works out for us. So 2 of those would mean I need 2 of these and 2 of these. So 2 sulfurs on both sides, 4 hydrogens on both sides, and I have 4 plus 2 plus 2, I have 8 oxygens on both sides. So that actually does work out pretty nicely. It's a 2, 1, 2, 2. That was just kind of tough to balance. I just had to use my gut for that one. But what mass of sulfur dioxide is needed to react with 37.50 moles of oxygen? So again, just start with whatever they give you, 37.50. And go from there. Right? If they give you moles, you're going to go right into a mole ratio. I want to know about the sulfur dioxide, so I have to do a ratio with sulfur dioxide. And that's a 2 to 1 ratio. So I can get this moles of oxygen to cancel out. And then I'll do one more step, because I need to multiply by a mass. This time I might have to actually do a little calculating. Oxygen is going to be 16, so double that is 32. Trying to figure out what 1 mole of that sulfur dioxide might weigh. So 2 oxygens is 32 plus sulfur is 32 also. If I check a periodic table here, it's 32.065. So I'll add on a 32.07. So my molar mass would be 64.07 grams per mole for that sulfur dioxide. So if I set up my work like this, everything cancels appropriately. I'm going to get a mass of sulfur dioxide, so I just got to multiply and divide. 37.5 times 2 times 64.07. Don't have to divide by ones because it doesn't change anything. It's going to give me a mass of it's really big, 4,800 5 and 25 hundredths, right? So 4,805.25. I need to round that appropriately because I don't need that many sig figs. Remember, it's been a while since we did this kind of stuff, but these whole numbers don't affect your rounding at all. You only have to worry about the other two numbers in this problem, and that's what makes me round to 4 sig figs, because both of those other numbers have 4 sig figs. So it's going to be that 4,805. So 4,805 grams of sulfur dioxide, which is pretty big. That'd be like about 5 kilograms. Should be like 2.5 pounds. So sizable amount of that sulfur dioxide in this reaction. Okay, so I'll do one more with you. You can do the other one on your own. But chlorine gas can be produced by passing an electric current through a concentrated solution of sodium chloride. So you got this brine solution, you run some electricity through it, you get what you need. You get your sodium hydroxide products and chlorine gas and hydrogen gas. But balancing, I see the chlorine is off, so I probably need a 2 over here. That means that I need 2 sodium hydroxides and actually 2 waters. Everything should be balanced on both sides. There's 2 sodiums, 2 chlorines, there's 4 hydrogens on both sides, yeah, and 2 oxygens, so we're good. So it's 2, 2, 2, 1, 1, balancing. So then from here, I just start with what's given to me, grams of sodium chloride. And it says you're starting with 250 grams of that sodium chloride. And this is the kind of problem where I wasn't given moles right away, so I'm going to have to get moles, because you always have to work through moles in a stoichiometry problem. So if it's not given to you, you have to get it some way, somehow. So you're going to have to divide by a molar mass. Sodium chloride has a molar mass of, let's see here, 22.99 plus 35.45 gives me 58.44 grams per mole. Again, I like to label these things completely to start with so I can keep track of everything, because I want to get rid of grams and get moles, and that's how I know that I did this backwards. I have to flip this over, right, because I need to divide by this value. So let me fix that real quick. Not bad. 58.44 grams per mole. So grams cancels. I now have moles of sodium chloride. But I want to know how many moles of chlorine are produced, right, and or hydrogen. Now, if you're paying attention and following along at home, the chlorine and hydrogen are in a 1-to-1 ratio. So either way, I'm going to get the same answer. From here, I just do one more step. I just have to do a ratio from sodium chloride to my chlorine or the hydrogen. It really wouldn't matter which one first. So I'm going to do the chlorine. It's always 1 mole of chlorine according to the equation per 2 moles of sodium chloride. So working this out, I just have to take the 250 divided by 58.44 divided by 2, and I should get my answer. it's going to be at 2.138. Let it be a 9.4, whatever. But I need to round this appropriately, so I can only use 2 sig figs from this number here. So I should round it to 2.1 of chlorine. Right? And again, I actually do know that it's also going to be 2.1 moles of hydrogen gas. But I told you guys yesterday that I'm not going to give you guys credit for anything if you don't show me any work. Now, that is a scenario where you don't really need to show a whole set of work. You don't have to do railroad tracks. But what you can do next to this is just put in parentheses 1-to-1 ratio. Because anytime that's true, the 2 mole values should be the same. You don't have to do a whole set of work, but you probably should tell me that just to make sure I know how you got that answer, because I'm always going to take off points if you're not going to show me work. So simple enough. I got answers for moles of chlorine gas. I got moles of hydrogen gas, 2.1 for both. So you just need to try to work your way through this one on your own, right? This one is the type where you go all the way from grams of one thing to grams of another. So although I only had 2 steps to my dimensional analysis on this slide, the next slide you're going to have to go 1 more step. Just as a hint. Because you don't want moles, you want grams of something. So you're going to multiply it by some value, some molar mass, right? That's grams per mole, so you can get grams as an answer. Otherwise, it would look very similar to this setup on this slide. So come up with an answer for this on your own. And I'll have you guys fill out a quiz to tell me what you got for that answer so I know that you worked it out. But otherwise, you got worksheets to do. Finish that little quiz to show me you watched your notes. We should be good.